Imagine you stumble upon an old family photo album. You see a picture of your grandmother, and right next to it, her mother. You keep turning the pages until you find a photo of your great-grandmother. And then, you find a picture of her son, dated a year before she was even born. Impossible, right? Well, this is the exact paradox astronomers found themselves facing. They discovered a star that, based on all the initial calculations, appeared to be older than the universe itself. How is that even possible? Is all of modern cosmology one big mistake? Today we're going to venture into deep space to unravel this astonishing mystery. This is the story of the star named Methuselah, a celestial body that challenged the very foundations of our understanding of time and space. Get comfortable. This calming journey will guide you through one of the greatest riddles in astrophysics. And I promise you, by the end of our trip, you'll look at the night sky completely differently. Before we dive into the heart of this cosmic paradox, let's establish the necessary context. We need to understand exactly what we mean when we talk about the age of the universe. According to the standard cosmological model, our universe was born in the Big Bang approximately 13.8 billion years ago. This number wasn't just pulled out of thin air. It comes from numerous independent observations, the primary one being the analysis of the cosmic microwave background, the echo of the Big Bang itself, which still permeates all of space. Spacecraft like the Planck satellite have measured this radiation with incredible precision, allowing us to calculate the age of creation. This age, 13.8 billion years, has become a fundamental limit. Nothing in the universe can be older than the universe itself. This is a basic law, like the cause always preceding the effect. And yet, against the backdrop of this seemingly unshakable truth, our main protagonist enters the scene, a star known by the catalogue number HD 10283, a star that dared to challenge time itself. So let's take a closer look at the source of all this scientific commotion. The star is officially named HD 10283, but astronomers affectionately call her the Methuselah Star. This name is a tribute to the biblical figure who supposedly lived for 969 years, a symbol of incredible longevity. And the name couldn't be more fitting. It's located relatively close to us in the constellation Libra, at a distance of about 190 light-years. This proximity makes it an object we can study in great detail. Unlike distant galaxies, whose light takes billions of years to reach us, Methuselah is essentially our cosmic next-door neighbor. It is classified as a subgiant, a star that has already burned through all the hydrogen in its core and is currently in a transitional phase before evolving into a red giant. But the most fascinating thing about this star is its chemical composition. It belongs to what astronomers call population 2 stars, which is essentially shorthand for extremely old. Its composition contains extremely few of the heavy elements that astronomers refer to as metals. This is a sure sign that it formed at the dawn of time, created from the primordial gas left over after the Big Bang, before the universe had time to enrich itself with elements heavier than hydrogen and helium. Just imagine. This star is nearly as old as the universe itself, a witness to its youth. It watched the first galaxies take shape and saw billions of other stars ignite and fade. And this ancient witness presented scientists with a startling surprise, one that forced them to question their own methods and even the accepted age of the universe itself. It is this extreme age and unique composition that became the key to the paradox. By observing it, astronomers peered into the past, but what they saw initially defied all logic. It was like discovering a living dinosaur wandering through a modern city, something that, by all accounts, simply shouldn't exist. So, how do scientists actually figure out how old a star is? It's far from a simple task. A star doesn't come with a birth certificate, and obviously it can't just tell us when it first ignited. The entire process resembles complex detective work, requiring us to piece together the whole picture using only circumstantial evidence. One key method involves diving deep into the stellar life cycle. We understand that stars, much like living beings, are born, live, and eventually expire. Their lifespan is primarily determined by their mass. The more massive the star, the quicker it burns through its fuel, resulting in a much shorter life. Our target star, Methuselah, is low mass, which means it should be extremely long-lived. Scientists rely on sophisticated computer models of stellar evolution. These models, grounded in the laws of nuclear physics, thermodynamics, and gravity, predict precisely how a star's brightness, temperature, and size evolve over vast stretches of time. By comparing the observed characteristics of a star, its luminosity and temperature, for example, with the model's predictions, astronomers can pinpoint exactly what stage of its life cycle it's currently in, and from there, estimate its age. To do this successfully, they must know two absolutely critical parameters: the star's actual brightness, its intrinsic luminosity, and what it's made of, its chemical composition. And that's where the complications begin. To determine the intrinsic luminosity, you must first know the star's precise distance. Logically, the farther away an object is, the fainter it appears. Determining the chemical composition, meanwhile, requires meticulous analysis of the light coming from the star, specifically its spectrum. It was precisely in these two areas, measuring distance and analyzing composition, that the resolution to the Methuselah paradox lay hidden. Initial estimates conducted decades ago yielded a truly staggering result. The star's age was calculated to be 16 billion years. 16 billion? That is over 2 billion years more than the accepted age of the entire universe. This was absolutely impossible and created a massive dilemma. Either we had to drastically revise the age of the universe or admit there was a fundamental flaw in our understanding of stellar evolution. Let's pause our discussion of the star for a moment and focus on how we measure distances in the cosmos. This concept is a cornerstone of all astronomy. Without accurate distance measurements, we can't truly understand the actual size, intrinsic brightness, or age of any celestial object. Imagine you're looking at two lights in the dark. One appears bright, the other dim. Which one is actually more powerful? Maybe the dim light is an incredibly powerful source that's just very far away, while the bright light is weak but close by. Without knowing the distance, you can't answer that question. It's the same challenge we face with stars. The fundamental and most trusted method for measuring distances to nearby stars is called the parallax method. The underlying principle is quite straightforward. Hold out your arm and look at your thumb, alternating between your left and right eye. You will notice your thumb appears to jump or shift against the distant background. That apparent movement is known as parallax. By knowing the distance between your eyes, which acts as the baseline, and measuring the angle of that shift, you can accurately calculate the distance to your thumb. Astronomers do the exact same thing, but instead of using the distance between two eyes, they use the vast distance the Earth travels as it orbits the Sun. They observe a target star at one position in the orbit, for example, in January, and then repeat the observation 6 months later, in July, when the Earth has moved halfway across its path to the opposite side of the Sun. The nearby star will appear to shift its position slightly against the backdrop of extremely distant, effectively stationary stars. By accurately measuring this tiny angle of apparent shift, simple trigonometry allows them to calculate the precise distance to that star. The larger the measured parallax, the closer the star is. The inherent challenge, however, is that these angles are impossibly small. Even for the very nearest stars, we are dealing with angular shifts that amount to mere fractions of an arcsecond. To put that into perspective, it's like trying to spot a coin placed several kilometers away. For many years, the precision of these measurements was low, which introduced significant errors into distance calculations and consequently into estimates of stellar luminosity and age. It was precisely this initial imprecision in measuring the parallax of the Methuselah star that contributed directly to its anomalously high calculated age. Let's now turn our attention back to our mysterious star. Early attempts to determine its age, conducted a while ago, famously led to a paradoxical result: 16 billion years. The scientific community was baffled. The first reaction, naturally, was to look for errors in the data. Was the distance perhaps measured incorrectly? Or were the stellar evolution models, which worked so well for other stars, failing when applied to such an ancient object. A new, more precise approach was desperately needed, and that perspective was provided to humanity by the Hubble Space Telescope. Launched into orbit in 1990, Hubble operates beyond Earth's distorting atmosphere, allowing it to take measurements with unprecedented accuracy. One of its key missions was specifically to refine the cosmic distance scale, notably through the parallax method. A team of astronomers led by Howard Bond aimed Hubble at the Methuselah Star and spent several years meticulously tracking its position. They utilized the telescope's specialized fine guidance sensors, allowing them to measure the parallax with surgical precision. These new data revealed that the star was slightly farther away than previously estimated, and if it's farther away, then given the same apparent brightness, its true luminosity must actually be higher. It was in fact brighter than initially supposed. This shift, while seemingly minor, had a cascading effect on the calculation of its age. In stellar evolution models, a brighter star burns its fuel faster. Therefore, to reach its current developmental stage, it must have required less time. The new calculation, based on Hubble's refined distance measurement, yielded a different figure. The star's estimated age got younger, dropping to 1446 billion years. This was a much better result. The gap between the star's age and the known age of the universe had narrowed, but the paradox stubbornly remained. 14.5 billion years is still significantly greater than the universe's accepted age of 13.8 billion. The problem wasn't solved, but scientists knew they were heading in the right direction. It became clear that the devil truly was in the details, specifically the measurement uncertainties. Okay, so the distance was refined, but the star still seemed impossibly old. We had to dig deeper. The next piece of evidence in our cosmic detective story was Methuselah's chemical composition. As we mentioned, this is an extremely metal-poor star. Let's break down what that means and why it's so critical. In astrophysics, the term metals is used to describe any element heavier than hydrogen and helium. Immediately following the Big Bang, the universe was composed almost entirely of these two lightest elements. Everything else, the oxygen we breathe, the carbon that forms our bodies, the iron in our blood, was forged later, deep inside stars. When massive stars explode as supernovae, they scatter these newly forged heavy elements throughout the cosmos. This enriched gas then forms the next generations of stars. Therefore, the younger a star is, the more metals it contains. Our Sun, for example, is a relatively metal-rich third-generation star. Methuselah, however, belongs to the most ancient population. It has very few heavy elements, but one specific element turned out to be particularly important: oxygen. Initial models assumed a specific ratio of oxygen to iron within the star. However, later and more precise spectroscopic analyses revealed that Methuselah actually contains more oxygen than previously thought. This discovery became the second key piece of the puzzle. Why does oxygen content influence age so dramatically? The key is that oxygen, along with other elements, affects the opacity of the stellar material and the speed of the nuclear reactions in the star's core. A higher amount of oxygen means that the core's hydrogen fusion proceeds slightly slower. The star, figuratively speaking, burns its fuel more economically. And if it burns slower, it requires a longer period of time to reach its current stage of evolution. This effect had to be factored in, but at the same time, it complicated the picture. On one hand, refining the distance made the star look younger. On the other, refining the chemical composition seemingly should have made it older. Scientists were forced to completely revise their models to account for both factors simultaneously. At this point, the story of the Methuselah Star transforms into a lesson about how real science truly operates. It's not a path from one breakthrough insight to the next. It's a painstaking process of accounting for minute details, constantly refining models, and admitting your own measurement errors. Let's talk about the concept of error or uncertainty in measurement. No scientific measurement is ever perfectly precise. There is always a range within which the true value most likely lies. When scientists state the age of the universe is 13.8 billion years, they mean that value plus or minus tens of millions of years. The same applies to the star's age. When the initial estimate pegged the star at 16 billion years, that figure also carried an error margin, say plus or minus 1 or 2 billion years. But even accounting for that large margin, the lower bound of the star's age was still higher than the upper bound of the universe's age. Their ranges simply did not overlap. The researchers' core task was to refine their measurements and aggressively narrow those uncertainty ranges. Working with Hubble data allowed them to significantly reduce the error margin in the distance measurement. New spectroscopic data helped narrow the uncertainty regarding the chemical composition. The next necessary step was combining all this updated data into a single, self-consistent model. A team of astronomers, once again led by Howard Bond, took on this complex challenge. They constructed a new, enhanced model for the evolution of the star HD 140283. This model integrated the latest findings, the refined distance, the new oxygen abundance, and other subtle effects that had previously been neglected. They accounted for the possibility that the star was born in a dwarf galaxy that was later absorbed by our Milky Way, which could have influenced its initial composition. They also completely revised the nuclear reactions occurring inside stars of this type. It was a monumental undertaking, requiring thousands of hours of computer modeling. Following all these extensive refinements and recalculations, Howard Bond's team finally published their updated, and at that time definitive, estimate for the age of the Methuselah Star in 2013. The result they reached was truly elegant, a new age of 14.27 billion years. At first glance, this figure still exceeds the universally accepted age of the universe, 13.8 billion years, had the paradox remained unsolved. However, the crucial element wasn't the absolute number, but the error margin. By utilizing the most precise data available and refining their stellar models, the researchers managed to dramatically narrow the range of uncertainty. The new margin of error was a mere plus or minus 800 million years. What does this imply? It means the star's true age most likely falls somewhere between 13.47 billion and 15.07 billion years. Now consider the age of the universe itself. 13. 8 billion years plus or minus only a few tens of millions. For the very first time, the lower bound of the star's potential age overlapped with the universe's age. The paradox that had plagued astronomers for decades was finally resolved, or at the very least it ceased to be a screaming contradiction. Methuselah was no longer an impossible object. Instead, it was revealed to be a simply, incredibly, extremely old star, born at the very dawn of time, perhaps just a few 100 million years after the Big Bang itself. While its age remains at the absolute upper limit of possibility, it no longer fundamentally violates the laws of cosmology. This provided immense relief to the entire scientific community. The story of Methuselah became a true triumph of the scientific method, demonstrating how persistence, precision, and the willingness to revise fundamental models ultimately lead to the solution of the most complex cosmic mysteries. Let's take a deep dive into the physics of stellar interiors to understand how seemingly minor details, such as the amount of oxygen present, can fundamentally impact a star's lifespan. Imagine the core of a star as a gigantic thermonuclear reactor. Inside, under immense pressure and temperature, protons, which are hydrogen nuclei, fuse together, forming helium nuclei. This process, known as the proton-proton cycle, is the primary energy source for stars like our Sun. However, in more massive and hotter stars, a different mechanism predominates, the so-called CNO cycle, or carbon-nitrogen-oxygen cycle. In this cycle, the nuclei of carbon, nitrogen, and oxygen act as catalysts. They participate in a chain of reactions, helping protons fuse into helium, but they are not ultimately consumed in the process. In very old, metal-poor stars like Methuselah, the CNO cycle plays a minor role. But the presence of even a small amount of these elements still affects the overall burn rate. The elevated oxygen content found in Methuselah slightly alters the balance of the reactions. Crucially, this affects the so-called opacity of the stellar material. Imagine trying to see through frosted or cloudy glass. The cloudier it is, the less light passes through. It's the same inside a star. The energy born in the core must push its way outward through layers of plasma. The chemical composition of that plasma determines how transparent it is to radiation. Oxygen and other heavy elements make the plasma more opaque. This means that energy gets trapped inside the star for longer. The internal layers heat up slightly more, causing the star to subtly inflate, and the temperature in its core to drop marginally. A decrease in core temperature, even by a fraction of a percent, results in the thermonuclear reaction rate slowing down. The star begins to burn its hydrogen reserves much more economically. It's like slightly easing up on the gas pedal in your car. You'll drive a little slower, but your fuel will last for a much longer journey. And that is how refining the oxygen content, a seemingly purely chemical parameter, directly impacts the star's mileage, or its overall age. But what if the issue wasn't just the star, but our very understanding of the universe's age? This was another question that plagued scientists. After all, the accepted figure of 13.8 billion years has its own margin of error and is fundamentally based on specific cosmological models. The main parameter determining the calculated age of the universe is the Hubble constant. This value describes the rate at which the universe is currently expanding. Logically, the faster it expands, the less time it took to reach its present size, meaning the universe must be younger. Conversely, if the expansion is slower, the universe is older. The problem is that in recent years, a serious discrepancy has emerged between measurements of the Hubble constant obtained through different methods. One method, based on studying the cosmic microwave background radiation, CMB, using the Planck telescope, yields one specific value. A different method, which relies on observations of supernovae and Cepheid variable stars in nearby galaxies, yields a value about 9% higher. This discrepancy, known as the Hubble tension, is one of the greatest puzzles in modern cosmology. It may indicate that something is fundamentally missing from our standard cosmological model. Perhaps we don't fully understand the nature of dark energy, the mysterious force responsible for the universe's accelerated expansion, or perhaps there are unknown particles or interactions yet to be discovered. If the higher value for the Hubble constant proves correct, the age of the universe would have to be revised downward, bringing it closer to 13 billion years. In that scenario, the Methuselah Star paradox would once again intensify. However, if the Planck data holds true, the age of 13.8 billion years remains valid. Thus, the story of this ancient star is tightly interwoven not only with stellar physics, but also with the most fundamental questions about the structure and evolution of the entire cosmos. It has truly become a litmus test for the robustness of our cosmological theories. The saga of Methuselah, the oldest known star, offered several profound lessons to the scientific community. First, it dramatically underscored the paramount importance of precision in astronomical measurements. A seemingly tiny deviation, a fraction of an arc-second in a parallax reading, or a few tenths of a percent difference in elemental composition, can translate into an age discrepancy spanning billions of years. This reliance on precision showcases the incredible power of modern technology, particularly instruments like the Hubble Space Telescope and its successor, the James Webb Space Telescope, which allow us to gaze into the cosmos with unprecedented detail. Secondly, the star demonstrated that even our most robust theoretical models consistently require rigorous testing and refinement. Standard stellar evolution models, while excellent at describing sun-like stars, proved inadequate for extreme outliers, specifically incredibly old and metal-poor stars. The Methuselah paradox forced theorists to revisit their calculations, integrate new physical effects, and ultimately create models that were both more precise and universally applicable. Thirdly, the star's history serves as a perfect illustration of how contradictions and paradoxes propel scientific progress. When empirical observations clash with established theory, this isn't a crisis point. It's a powerful catalyst for deeper inquiry. It is precisely impossible objects like Methuselah that push scientists beyond conventional thinking forcing them to locate weaknesses in existing theories and ultimately leading to a more profound understanding of the universe. Far from breaking cosmology, as some initially feared, the star actually strengthened it. By passing this ultimate stress test, the standard cosmological model and the theory of stellar evolution emerged more robust and reliable. We can now speak with far greater certainty about both the age of the universe and the life paths of the very first stars that ignited within it. Let's quickly review the entire sequence of reasoning that ultimately resolved this famous paradox. Imagine the scales of justice. On one side, we have the highly precise age of the universe, 13.8 billion years. On the other side sits the age of the Methuselah Star. Initially, that side was heavily weighted, suggesting an age of 16 billion years. Scientists faced the challenge of either lightening the star's side or heavily weighting the universe's side. Step 1. Re-evaluating the distance using the Hubble Space Telescope. The star was found to be farther away, meaning it was inherently brighter. A brighter star burns through its fuel faster, meaning it evolves quicker. This discovery effectively removed about 1.5 billion years from its estimated age. The star's age dropped to 14.5 billion years. The scales were closer to balance, but the discrepancy was still noticeable. Step 2. A refined look at the star's chemical composition. It turned out the star contained more oxygen than previously assumed. This chemical makeup, conversely, slows down stellar evolution. This factor added several 100 million years back onto the star's side of the scales. The situation was complicated once again. Step 3. Building a comprehensive model. Scientists weren't simply adding and subtracting years anymore. They developed a new, holistic model that simultaneously accounted for the revised distance, the new chemical composition, and other subtle physical effects. This didn't just yield a single number, but rather a most probable value with clearly defined error margins. The final calculation settled on an age of 14.27 billion years, plus or minus 800 million years. Critically, this wide margin meant the star's true age could be as low as 13.5 billion years. This range finally overlapped with the established age of the universe. The scales reached equilibrium. The contradiction vanished. The Methuselah Star, once an impossible anomaly, transformed into an invaluable scientific treasure. One of the oldest known stars whose age we have been able to measure with astonishing precision. It's crucial to understand that Methuselah-type stars are genuine time capsules. They hold vital information about the chemical composition of the early universe. By studying their spectra, we can literally read the recipe of the cosmos from that distant epoch. The star's incredibly low metallicity confirms that it formed from the primordial, almost pure, hydrogen and helium gas. But even the tiny traces of heavy elements found within it can reveal astonishing secrets. For instance, the ratio of these elements can indicate exactly which types of supernovae exploded before the star's birth, enriching the surrounding environment. These were potentially the massive, short-lived, first-generation population 3 stars, which we still cannot observe directly. The Methuselah Star, therefore, acts as a kind of cosmic fossil, carrying the fingerprints of those very first, long-extinguished luminous bodies. Its existence and unique properties impose significant constraints on our theories about the early universe. For example, the fact that it does contain even small amounts of metals tells us that at least one prior generation of massive stars must have been born, lived its life, and exploded before Methuselah ever formed. This implies that star formation processes began in the cosmos incredibly early, potentially just 100 or 200 million years after the Big Bang. Every such ancient star we locate and study is another piece of the puzzle, helping us reconstruct the complete picture of cosmic history from its absolute beginning right up to the present day. And Methuselah, with its paradoxical story, has proven to be one of the most crucial and informative pieces in that entire grand cosmic endeavor. Could a star actually exist that is genuinely older than the universe itself? From the perspective of modern physics, the answer is no. This would violate one of our most fundamental laws, the principle of causality. The universe, as a unified system, is the root cause for everything within it. Objects inside that system simply cannot predate the system itself. If we proved with absolute 100% precision and zero error that the Methuselah Star was, say, 15 billion years old while the universe was only 13.8 billion, this wouldn't just be a scientific puzzle, it would mean the total collapse of the standard cosmological model. We would have to admit that our fundamental understanding of the Big Bang is completely wrong. Perhaps it would point to the existence of a multiverse, suggesting that Methuselah had flown in from some older, adjacent universe. Or maybe it would mean the Big Bang wasn't the ultimate beginning, but merely one stage in an infinite cycle of expansion and contraction, making Methuselah a relic of a previous cycle. These are, of course, highly exciting but purely hypothetical scenarios. Currently, we have zero observational data to back any of them up. The history surrounding Methuselah showed us that a far more likely explanation for such paradoxes is simply the incompleteness of our knowledge and the inherent inaccuracies in our measurements. Science prefers to move forward incrementally, refining existing theories rather than discarding them at the first sign of contradiction. So, while the idea of a traveling star from another universe certainly sparks the imagination, the real, though far more prosaic explanation lay in refining the data and perfecting our models. The paradox wasn't inherent in nature itself, but in how we described it. That is a crucial point, and it demonstrates the maturity of modern science. Let's talk about the future of research into these kinds of celestial objects. The saga of Methuselah hasn't ended yet. Even though the main age paradox has been resolved, scientists are continuing to study this star and others like it with unprecedented precision. New instruments, such as the James Webb Space Telescope, are unlocking incredible possibilities for us. Webb operates in the infrared spectrum, allowing it to peer into the dustiest, most distant corners of the universe, the stellar nurseries where stars are born. It is also capable of conducting spectroscopic analysis with previously unattainable levels of detail. This means we will be able to determine the chemical composition of ancient stars much more precisely, measuring the abundance of not just oxygen, but dozens of other elements. This, in turn, will further refine our models of stellar evolution. Another critical area of research is astroseismology. Scientists have learned to study the internal structure of stars using their starquakes, the tiny oscillations on their surface. These pulsations, similar to seismic waves on Earth, carry information about what's happening deep inside the star, revealing the size of its core and the processes of material mixing. Analyzing these oscillations can provide an independent and highly precise estimate of a star's age. Perhaps in the future, we can apply astroseismology techniques to Methuselah itself, providing yet another confirmation of its true age. Furthermore, astronomers are actively searching for other extremely old stars within our galaxy. Every single discovery is an invaluable source of data. By compiling a comprehensive census of these most ancient stars, we can better understand the conditions under which they formed and reconstruct the history of the earliest stages of our Milky Way's life. So, the story of Methuselah isn't the end, it's just the beginning of a new chapter in cosmic archaeology. Let's now consider another key aspect of stellar evolution, crucial to resolving this paradox: the process of element diffusion within a star. Imagine a simple analogy, a glass of water with a drop of ink. Eventually, the ink spreads evenly throughout the volume. A comparable, though far more complex process unfolds within stars. Under the influence of gravity, heavier elements, like helium or metals, in astronomical terms, tend to slowly migrate toward the stellar core. This phenomenon is formally known as gravitational settling or element diffusion. Consequently, the surface layers of the star gradually become depleted of these heavy elements over time. Crucially, when we perform spectral analysis, we are measuring the chemical composition only of these outer layers. If we fail to account for diffusion, we draw the wrong conclusions about the star's initial composition. We assume the star started out with fewer metals than it actually had. This misinterpretation, in turn, leads to an inflated age estimate because we know that stars with lower metallicity evolve at a slower rate. In the most recent stellar evolution, models used to refine the age of the Methuselah Star, the diffusion effect was carefully incorporated. Scientists had to calculate the exact fraction of heavy elements that had settled into the stellar interior over billions of years and apply the necessary correction. And this is yet another illustration of just how subtle and intricate modern astrophysics is. We must account for not only the nuclear reactions happening in the core, but also slow material transport, convection, stellar rotation, and even its magnetic fields. Each of these factors makes a crucial contribution to the overall picture, and only by considering them jointly can we achieve results that genuinely match observational data. Ultimately, the puzzle presented by the Methuselah Star forced theoretical physicists to focus intently on these seemingly secondary effects, drastically improving the realism and accuracy of their stellar models. The movement of the Methuselah Star through space has given scientists crucial clues about its origins. HD 140283 isn't just an ancient star, it's also a prodigious cosmic traveler. It rockets through our galaxy at an astonishing speed, approximately 1.3 million kilometers per hour. What's even more striking is its highly unusual orbit. Unlike our Sun, which maintains a nearly circular path within the flat plane of the galactic disk, Methuselah follows a highly elongated elliptical trajectory. This orbit slingshots it far beyond the galactic disk itself, deep into the region known as the galactic halo. The halo is a vast spherical shell surrounding the Milky Way, populated primarily by extremely ancient stars and globular clusters. This unique speed and location are telltale signs that Methuselah was not born in its current neighborhood. It is almost certainly an interstellar immigrant. The most plausible theory, as previously mentioned, is that the star originated in a small satellite dwarf galaxy. Billions of years ago, this smaller galaxy was captured and devoured by the gravity of our much more massive Milky Way. During this galactic merger, the dwarf galaxy's stars were gravitationally stripped or ripped apart and scattered throughout the Milky Way's halo, all while retaining their highly unusual elongated orbits. This hypothesis neatly explains its high velocity, its bizarre trajectory, and its unique chemical fingerprint, which differs subtly from the composition of stars originally formed within our own galaxy. By studying these stellar newcomers, we can reconstruct the formation history of the Milky Way, which we now understand grew to its current immense size by consuming its smaller neighbors. Methuselah is a living witness to these ancient acts of galactic cannibalism. Its story is not just the biography of a single star, but the history of an entire galaxy that was erased from the cosmic map, leaving behind only a handful of stellar orphans. Let's go back to the very beginning, to the Big Bang. What do we know about the first stars that lit up the universe? Theory predicts they must have been vastly different from the stars we see today. These hypothetical objects, called population 3 stars, formed from absolutely pristine gas, consisting only of hydrogen and helium. Without heavy elements, which typically help gas cool and collapse, these protostellar clouds could grow to enormous sizes. Consequently, the first stars must have been absolute monsters, hundreds of times more massive than our own Sun. Because of their immense mass, they lived incredibly short lives, perhaps just a few million years. They burned through their fuel at a furious pace, eventually exploding as supernovae, sowing the universe with carbon, oxygen, iron, and other heavy elements for the very first time. It was from the ashes of these first stars that the next generation formed, the population 2 stars, which includes objects like Methuselah. The fact that Methuselah still contains a small trace of metals is indirect evidence for the existence of that first, long-vanished generation of stars. It represents the oldest stellar generation still alive today. Finding a true population 3 star, one composed purely of hydrogen and helium, is the holy grail for modern astronomers. So far, none of these objects have been definitively detected. Perhaps they were all too massive and perished long ago. Or maybe they are so exceedingly rare that we simply haven't located them yet. But studying stars like Methuselah allows us to get closer to the era of cosmic dawn, when, following the profound darkness that reigned after the Big Bang, the first lights flickered on in the universe. Methuselah is a bridge connecting us to that incredibly distant and mysterious era. It's fascinating to ponder all that this star has witnessed throughout its incredibly long existence. When Methuselah first ignited, the cosmos was a dramatically different place. It was smaller, denser, and much, much hotter. Galaxies were only just beginning to coalesce from gigantic clouds of gas. Our Sun and Earth were nowhere to be found. They wouldn't even appear for another 9 billion years. Methuselah was a prime witness to the era of active galaxy formation, seeing their violent mergers and collisions firsthand. It watched as countless generations of stars were born and died, each generation contributing to the enrichment of the cosmos with heavier elements. It survived the age of quasars, when the supermassive black holes at the centers of galaxies were at their most active, spewing out powerful relativistic jets. Over its lifetime, the universe has not only expanded tens of times over, but its fundamental nature has changed. It became more structured, significantly colder, and, perhaps paradoxically, much darker as the rate of star formation steadily slowed down. And here we are, more than 13 billion years later, having emerged on a planet orbiting an otherwise unremarkable yellow star, nestled in the outskirts of one spiral galaxy. Using the tools we've built, we are able to look back at this ancient witness and actually read its history. It is an absolutely astonishing realization. The light we capture today from Methuselah left the star only 190 years ago, yet the star itself carries information about events that transpired over 13 billion years ago. By studying it, we undertake a genuine form of time travel, peering deep into the ancient past of our cosmos. That tiny pinprick of light in the night sky is not just a star, it is a living archive holding the secrets to the birth and infancy of our universe. A question you might be asking is, why are we so certain about the theory of stellar evolution? What if it's fundamentally wrong and stars operate by completely different rules? This theory isn't just a collection of speculative ideas. It's built on the solid foundation of physical laws verified right here in Earth laboratories: nuclear physics, quantum mechanics, thermodynamics, and the theory of radiative transfer. Most importantly, it is constantly being tested by observation. Astronomers observe millions of stars caught at different stages of their life cycle. We see giant molecular clouds where new stars are being born right now. We see young star clusters where all the stars were born simultaneously but are evolving at different speeds depending on their mass. We observe main sequence stars like our Sun. We see red giants, white dwarfs, neutron stars, and black holes, all the final evolutionary stages predicted by the theory. All these observations combine to form a single, consistent picture that brilliantly confirms our theoretical models. Of course, the theory still has its gaps and unanswered questions. For instance, we don't fully understand the precise mechanism behind a supernova explosion or the exact processes of material mixing deep inside a star's core. But at its core, the theory of stellar evolution remains one of the most successful and rigorously tested theories in modern science. That's why, when the paradox involving the Methuselah Star arose, scientists didn't toss out the entire theory. Instead, they hypothesized that the problem lay in the details: inaccurate input data, such as distance or chemical composition, or the necessity of accounting for subtler physical effects that had previously been neglected. And subsequent research proved that approach to be absolutely correct. To finish up our look at the technical side, there's one more instrument we need to discuss that played a massive role in solving these kinds of astronomical mysteries. That is the European Space Telescope, Gaia. Launched in 2013, this spacecraft truly revolutionized astrometry, the science of measuring the positions and movements of celestial bodies. Its main mission is to create a three-dimensional map of our galaxy with unprecedented accuracy. Over the years, Gaia has measured the parallaxes and consequently the distances to over 1 billion stars in the Milky Way. Gaia's data helped refine the distance to the Methuselah Star, confirming and even improving upon the results gathered by Hubble. This provided scientists with even greater confidence in the accuracy of their calculations. But Gaia does much more than just measure distances. It also measures the proper motion of stars across the celestial sphere and their radial velocities, the speed at which they move toward or away from us. By combining all this data, we can construct a complete three-dimensional picture of a star's movement in space, mapping its entire orbit within the galaxy. It was Gaia's data that finally confirmed Methuselah is a halo star with a highly unusual orbit, strengthening the hypothesis of its extragalactic origin. Thus, we see how the work of seemingly unrelated space missions, Hubble, Planck, and Gaia, intertwines into a single tapestry of knowledge. Planck refined the age of the universe, Hubble and Gaia pinpointed the star's distance, and ground-based spectrographs determined its chemical composition. Only by bringing all these pieces of information together were scientists able to solve the complex puzzle the universe had presented them with. This is a perfect example of how modern big science operates. Breakthroughs are achieved not by lone geniuses, but through the efforts of vast international teams working with highly complex instruments. At first glance, the story of the Methuselah Star might seem like a highly specialized topic, relevant only to a handful of astrophysicists, but in reality, it touches on the deepest philosophical questions that have haunted humanity since the dawn of time. Where did we come from? How did the world we inhabit come to be? What is our true place within it? By attempting to measure the age of this ancient star, scientists are essentially trying to look beyond the horizon of our everyday experience to touch the very wellsprings of time itself. This story beautifully illustrates the simultaneous fragility and power of human knowledge. On one hand, the slightest inaccuracy in measurement can lead us to absurd conclusions, to paradoxes that challenge the entire framework of our understanding of the cosmos. On the other hand, we have the scientific method, a powerful tool that allows us to systematically correct our errors, filter out false hypotheses, and advance toward the truth, one step at a time. The Methuselah paradox is not a story of scientific failure, it is a story of scientific triumph. It demonstrates that science is a living, self-correcting process. Science is not afraid to admit its mistakes and revise its central tenets in the face of new evidence. And it is precisely this flexibility and intellectual honesty that makes it the most reliable method we have for understanding the universe. This tiny, faint star in the constellation Libra forced thousands of scientists worldwide to re-examine their data, refine their theories, and ultimately gain a deeper comprehension of the universe. This is its enormous, lasting significance. It reminds us that the cosmos is full of mysteries, and the most groundbreaking discoveries often await us precisely where we least expect them. Let's imagine an alternative reality where the paradox was never solved. What if all subsequent, most precise measurements had confirmed that the star was genuinely 2 billion years older than the universe, and we simply couldn't find any flaws in our models of stellar evolution? That would have triggered a massive revolution in physics, comparable only to the advent of relativity or quantum mechanics. The standard Big Bang model, which describes the universe as originating from a singularity 13.8 billion years ago, would have to be completely scrapped. Scientists would be forced to seek a new, fundamental theory. One alternative might have been the steady-state theory, popular back in the mid-20th century, which claimed the universe had no beginning and would exist eternally. Or, as we've already discussed, this could have provided strong evidence for cyclical models, where universes are born and die in succession. We might even have had to reconsider fundamentals like Einstein's general theory of relativity, upon which all modern cosmology is based. It's possible that on incredibly vast scales of space and time, gravity simply doesn't behave the way we currently understand it. Of course, these are all just fantasies, but they demonstrate just how high the stakes were during the whole Methuselah Star episode. A single object, one tiny star had the potential to overturn the entire edifice of modern science. The fact that we eventually managed to explain everything within the framework of existing theories, even though it required significant refinement, served as the strongest possible confirmation of our general understanding of the cosmos. Science survived this stress test and emerged even stronger and more confident in its foundations. Another fascinating aspect of this narrative is the evolution of the very concept of age within science itself. For ancient civilizations, the cosmos was essentially eternal and immutable. Then, following the rise of geology in the 19th century, scientists recognized that Earth had a vast history, first measured in millions and eventually in billions of years. In the early 20th century, Edwin Hubble discovered the expansion of the universe. This led to the revolutionary concept that the universe itself had a beginning, the Big Bang. Initially, estimates of the universe's age were very crude and severely underestimated, only about 2 billion years. This created a profound paradox, as geologists already knew that the Earth itself was far older. Over time, as observations and theoretical models improved, the estimated age of the universe grew and refined, settling on the modern figure of 13.8 billion years. Star dating techniques developed in parallel. And now, on this new frontier of scientific advancement, we have encountered the age paradox once more, but at a whole new level. This time, it wasn't Earth, but a single star that appeared older than the entire cosmos. Just as before, resolving this contradiction immediately led to a deeper and more accurate understanding of our reality. This entire history teaches us that our knowledge is never truly final. Each new generation of scientists, armed with better tools and fresh ideas, refines and completes the picture begun by their predecessors. It is highly likely that the future holds new, even more stunning paradoxes that will force us to fundamentally rethink our understanding of time, space, and the very nature of reality. The Methuselah Star is a permanent reminder that the universe will always be slightly more complex and infinitely more fascinating than even our most ambitious theories suggest. Are there other stellar long-livers, cosmic senior citizens, if you will, that challenge our current cosmological models? Yes, Methuselah is not alone, although it is certainly the most famous and well-studied example. Astronomers are finding an entire class of objects known as ultra-metal-poor stars, primarily located in the halo of our galaxy, which also demonstrate extremely great ages. Take, for instance, the binary system CS22892-052. One of these stars contains a record low amount of iron, yet it is enriched with other elements, a chemical signature that strongly suggests its formation in the very early universe. Another interesting object is the star HE 1327-2326, which at the time of its discovery was the most iron-poor star ever known. By studying a whole population of these stars, rather than just focusing on a single object, scientists can gather much more reliable statistical data and rigorously test their hypotheses. If Methuselah were the only object of its kind, we might dismiss it as a unique anomaly or a measurement error. But the existence of an entire class of similar stars confirms that star formation processes in the nascent universe truly did produce these ancient relics. By comparing the chemical makeup of these various ancient stars, astronomers can reconstruct the early universe's inherent non-uniformity. This helps them understand how the enrichment of heavy elements proceeded differently across various regions of space. Some of these stars may have been born in different dwarf galaxies that were later absorbed into the Milky Way. In essence, every single one of these stars is a cosmic archaeological artifact, allowing us to examine the cultural differences, the unique chemical signatures between ancient galaxies that have long since been absorbed and ceased to exist. Let's talk a little bit about the name itself, Methuselah. Names play a critical role in astronomy. Official designations like HD 140283 are merely catalogue numbers. They are useful for systematic classification but are entirely devoid of character. It's the unofficial, popular names, the monikers scientists give to truly intriguing objects that help make science more vibrant and relatable. The name Methuselah was proposed by the study's principal investigator, astronomer Howard Bond, and it instantly stuck. It perfectly captures the essence of the object, its incredible, almost biblical antiquity. This name creates a powerful image and helps communicate the complexity of a scientific discovery to a broad audience. After all, a news headline reading, "Evolutionary Model of Star HD 40283 Refined," would attract far less attention than "Methuselah Star's age no longer contradicts age of universe." This is a perfect example of how scientific communication leverages metaphor and vivid imagery to transform dry facts into a compelling story. The history of this star truly resembles an ancient myth or legend, the legend of an elder who remembers the dawn of time, whose very existence forced the wise men to question their established sacred texts. Only in this version, the elder is a distant star and the wise men are modern astrophysicists. These scientists, through sheer diligence and intellect, were ultimately able to unravel its mystery and secure its place in the great chronicle of the universe. This name is a tribute not just to the star's age, but to the colossal temporal scale modern science operates on, allowing us to mentally journey billions of years into the past. Let's try to visualize the incredible journey of this star. Picture the primordial cosmos only a few 100 million years following the Big Bang. It was a dark, almost empty expanse, filled only with giant, diffuse clouds of hydrogen and helium. Slowly, gravity began to pull these clouds together into denser knots. Inside one of these knots within a small protogalaxy, matter compacted so tightly that nuclear fusion ignited at its core. Our star, Methuselah, was born. It began its long journey shining dimly in a young, unstructured universe. There were no Earth-like planets around it. The necessary chemical elements simply hadn't been forged yet. For billions of years, it traveled along its highly elliptical orbit. During this time, its home dwarf galaxy collided with a much larger neighbor, the nascent Milky Way, and was ripped apart. Methuselah became a captive of this new, massive galaxy. It continued its journey within the Milky Way's halo, watching from afar as generations of stars formed and expired within the galactic disk, and as our own solar system was born. Deep within its core, hydrogen slowly but surely burned out. Its surface cooled, the star dimmed slightly, preparing for the next stage of its life. And then, near the close of its 13th billion year of existence, intelligent life emerged on one of the planets within the very galaxy that captured it. This life, a mere blink of an eye in cosmic time, aimed its telescopes at Methuselah and began to ask questions. For the star Methuselah, all of this is just a fleeting moment in its impossibly long life. It will continue its journey for billions more years before swelling into a red giant and finally fading into a cooling white dwarf. But for us, the chance to study it offers a unique opportunity to touch history itself and understand the very origins of our existence. Let's look at the question of how accurate our understanding is of the nuclear reactions that underpin our models of stellar evolution. This knowledge comes not only from theoretical calculations, but also from direct laboratory experiments here on Earth. Physicists use particle accelerators to collide atomic nuclei and measure the probabilities of various nuclear reactions at energies similar to those found deep inside stars. However, this is an incredibly complex challenge. The probability of these reactions occurring in stars is minuscule, and reproducing them in a lab, where the experiment lasts minutes instead of billions of years, is extremely difficult. Scientists must extrapolate data obtained at higher energies down to the low energies characteristic of stellar interiors, and this necessary extrapolation introduces a degree of uncertainty into our models. One such key reaction is the fusion of a proton with a nitrogen-14 nucleus, which represents the slowest link in the carbon-nitrogen-oxygen, or CNO, cycle. Even a slight refinement in the rate of this reaction can significantly alter the calculated lifetime of stars, and consequently, their estimated age. In recent years, physicists have managed to significantly increase the precision of these measurements, primarily by moving to deep underground laboratories where background cosmic radiation is minimized. These new, highly accurate data points have been incorporated into modern stellar models, including those used to calculate the age of the Methuselah Star. This highlights yet another example of how closely intertwined different fields of science truly are. To accurately determine the age of a star in distant space, we first need to descend deep underground and conduct highly complex experiments in nuclear physics. Astronomy, cosmology, and nuclear physics, they all work together to create a unified and consistent picture of the universe. Every time we refine a detail in one area, it echoes throughout all the others, allowing us to see the universe with ever-increasing clarity. To wrap up our long discussion, the Methuselah Star, HD 140283, presented science with what we call a perfect storm. Several factors converged in this one object, each contributing to uncertainty and pushing initial calculations toward a seemingly paradoxical result. First, there is its incredible proximity. Had the star been farther away, we simply wouldn't have been able to measure its parallax with sufficient accuracy, and the entire mystery wouldn't have been so acute. Second, its extreme chemical composition, a very low metal content, which instantly pushed it outside the boundaries of our standard, well-calibrated stellar models. Third, its precise evolutionary stage, the transition from the main sequence to a subgent. At this point, the star's luminosity is highly sensitive to its age. This allows us to determine the age with high precision, but simultaneously makes the calculations extremely susceptible to even tiny errors in the input parameters. And finally, the time period itself, the current epoch, where our observational technology has reached a level allowing us to measure all these variables with unprecedented precision. Hubble, Gaia, modern spectrographs, and powerful simulation computers, all these tools have appeared relatively recently. Decades ago, this paradox would have been an insoluble puzzle. Today, however, it stands as a triumphant example of the sheer power of the scientific method at work. The story of Methuselah is not just the story of one star. It is the story of how we, as humans, learn to read the universe's grand book, how we decode its language, correct our translation errors, and slowly, page by page, approach an understanding of its magnificent design. Let's end with one last, slightly speculative question. If Methuselah formed so incredibly early, could planets have developed around it or other similar first- or second-generation stars? And if so, could life have emerged on them? Traditionally, the answer has been no. To form rocky, Earth-like planets, you need heavier elements, silicon, oxygen, and iron. And for life, as we currently understand it, you need carbon, nitrogen, and water. The early universe was severely lacking in these elements. The gas clouds that formed Methuselah and its stellar siblings were simply too clean, or rather too pristine. However, some recent theories suggest that even under those conditions, massive gas giant planets similar to Jupiter might have been able to form. Even more exotic hypotheses propose the possibility of life based not on carbon, but on other elements, or perhaps even life existing within the atmospheres of these gas giants. Furthermore, the universe itself was warmer during that epoch. The cosmic background radiation was hot enough that liquid water could potentially exist on a planet's surface even without light from its parent star. This period is often referred to as the habitable epoch of the early universe. While this certainly skirts the edge of science fiction for now, the mere idea that life could have emerged in the universe far earlier than it did on Earth is truly captivating. Stars like Methuselah are the only remaining witnesses to that era. Who knows what other secrets they hold? Perhaps future studies of their planetary systems, should any be found, will reveal even more astonishing surprises than the paradox of their age. It reminds us that we are still only at the very beginning of our journey exploring the cosmos. Our journey to the oldest known star is drawing to a close. We've seen how a seemingly simple question, just how old is this star, unfolded into a genuine astrophysical cold case, challenging the very foundations of cosmology and stellar physics. We've explored the complex methods scientists use to gauge cosmic distances and stellar ages. We recognize the crucial role that margins of error and uncertainty play in the scientific process. And we witnessed how a seemingly intractable paradox was elegantly resolved through painstaking research, new observational technologies, and the refinement of our theoretical models. The Methuselah Star, HD 140283, is no longer a paradox. It has claimed its rightful place in history as one of the oldest and most compelling objects in our entire galaxy. While it is not older than the universe itself, it is its contemporary, its peer, a living memory of cosmic time. This entire narrative is an anthem to human curiosity and the power of intellect, enabling us, confined to one small blue planet, to unravel mysteries measured in billions of years. When you look up at the night sky, remember that every single point of light is much more than just a distant lamp shining in the darkness. It is a complex story, and some of those stories began almost at the very dawn of time, and we are only just beginning to learn how to read them. This knowledge doesn't make the universe any less mysterious. On the contrary, it infuses it with even greater meaning, profoundness, and grandeur. And perhaps that is the most essential lesson the ancient Methuselah Star has taught us all. So what was the final conclusion? The star that seemed older than the universe turned out to be simply very, very old. The paradox that threatened to unravel the foundations of modern cosmology was ultimately a result of imprecise measurements and incomplete theoretical models. This wasn't an error on the part of the scientists, but rather a crucial moment of growth, a catalyst that pushed them to develop more accurate instruments and more refined theories. The story of Methuselah is a perfect demonstration of how science operates. It doesn't look for easy answers, it seeks the truth, no matter how complex it might be. And along this path, contradictions and paradoxes are not obstacles, they are the most valuable guideposts we have. This ancient star helped us refine both the age of the universe and our knowledge of how the very first generation of stars lived and died. It became a key to understanding the early youth of our cosmos. I hope this journey back to the dawn of time was fascinating and perhaps helped you relax. Thank you for spending this time with me. If you enjoyed this cosmic story, please hit the like button and subscribe to the channel so you don't miss future sleep lectures on the mysteries of science. Now a question for you. What other impossible discoveries do you think await us in the depths of space? Let me know your predictions in the comments below. I'm very interested to read them. Good night and sweet dreams.